So, hello and welcome to today's ACM Learning webinar. This webcast is part of the ACM's commitment to lifelong I'm sorry, I'm not an English-speaking person, so sometimes I get stuck to this. So, this is part of ACM's commitment to lifelong learning and professional development, serving a global membership of computing professionals and students. I am Elisabetta Di Nitto, professor at Politecnico di Milano and vice chair of ACM SIGSOFT, and I am also an ACM member. My research interests and expertise lie in the area of software engineering, in particular model-driven engineering and self-adaptation applied to cloud-based applications and to data-intensive applications. So if you want to learn more about my background, you can check my bio. So for those of you who might be unfamiliar with ACM or what it has to offer, here is more information about this. ACM offers educational and professional development resources that bolster skills and enhance career opportunities. Our members can stay competitive in the constantly changing world of computing with a range of ACM Learning Center resources at learning.acm.org. You can see some of the highlights on your screen. So, before we get started, I would like to quickly mention a few housekeeping items shown on the slide in front of you. First, the slides will advance automatically through the event. On the bottom panel, you will find a number of additional widgets and resources. And if you are experiencing problems with the slides or audio, press the F5 key in Windows or Command+R if you are on Mac, or refresh your browser on a mobile device. Or you can close and relaunch the presentation. To control volume, adjust the master volume on your computer. If you have questions during this webinar, please type them into the Q&A box at any time during the webinar and click the Submit button. I will organize the questions as Bertrand speaks, and he will reserve some time at the end of the presentation to address them. So this session is being recorded and will be archived, so you will receive an automatic email notification when it becomes available. And check learning.acm.org for updates on this and other upcoming webcasts. At the end of the presentation, you will see a survey open on your screen. Please take a minute to fill it out to help us improve our webinars. You may also open the link to the survey at any time from the resources window on your screen. So you can use a Facebook and Twitter widgets on the bottom panel to share the presentation link with your friends, as well as tweet comments and questions using the hashtag ACMLearning. We will be watching for your tweets. We also have a new community discourse page to continue the discussion after this webcast, including questions we won't be able to get through during the Q&A session. So today's presentation is Concurrent Object-Oriented Programming by Bertrand Meyer. So Bertrand is a CTO of Eiffel Software and a professor at Politecnico di Milano and Innopolis University. He is the author of several bestsellers on software topics. His work on Scoop is supported by an advanced investigator grant by the European Research Council. And Bertrand is also ACM Fellow and ACM Software System Award recipient. So I'm very glad then to give the floor to Bertrand for this very interesting talk. Thank you.
Thank you very much, Elisabetta. It's a very nice introduction. I have the pleasure of being in magnificent Milan, in Italy, together with a few colleagues, including Professor Di Nitto, and so this is partly a live presentation. So I'm going to talk about a model of concurrent object-oriented programming called Scoop. The claims that we make for Scoop, to give you kind of the gist at the beginning, are the following. It guarantees the absence of data races. I'm going to come back to data races in a few moments, but I'm sure that many of you know what a data race is. It retains all the mechanisms of object-oriented modeling, so there's no need to renounce the beauties of object-oriented mechanisms, such as inheritance, for example. It guarantees fairness, which is important in concurrent applications, and it's quite high level. That is, it removes many concerns from the programmer. Sorry, I pushed the wrong slide. It removes many concerns from the programmer by providing a higher level of abstraction. It is not tied to a particular form of concurrency. It's actually quite wide in its application. It retains accepted patterns of reasoning about programs. So the idea is that you don't have to become a completely new programmer, learn completely new skills to become a concurrent programmer if you were a sequential programmer. And we feel that it's simple to learn and use. Of course, everyone says that, but it's not just hand-waving, in the sense that there are a number of empirical studies which have compared the learning of Scoop to the learning of other approaches to concurrency, and quite favorably. Let me also mention right away about performance, because for a number of years Scoop existed as a nice mechanism on paper with a prototype implementation which was not very fast, and this has now been fixed in the sense that over the past few years a number of people have worked very hard to make the implementation of Scoop very efficient. So you can see here, you can study later at your leisure, some statistics that were performed by some of my colleagues and published at ESEC-FSC a few years ago. And the basic idea, you see that smaller is better, is that Scoop holds its own with respect to all the other mechanisms for concurrent programming. It's in the head of the pack. Okay, so what is it? The acronym stands for Simple Concurrent Object-Oriented Programming. The basic ideas are not new. They go back to a communications VACN paper from 1993, and then it underwent various attempts at implementation, one at Eiffel Software in the 90s using processors, and then the current implementation comes from efforts at ETH Zurich and at Eiffel Software in the past 10 or 15 years. It benefited tremendously from an advanced investigator grant from the European Research Council called Concurrency Made Easy, which is proceeding, it's terminating soon. And it's not an experimental idea or a prototype anymore. It has become a standard part of the Eiffel language and the IDE, so both the language and the implementation. It's an incremental addition to the basic O schemes. It's about as minimal as it can get, since it's only one keyword. The general goal is very simply stated. We have developed over the past decades very good techniques for programming sequential applications. Of course, things are not perfect, but we have made tremendous advances as compared to how we were programming 20, 30, 40 years ago. And this does not apply yet to concurrent programming. So can we bring concurrent programming to the same level of abstraction and convenience as we have reached for sequential programming? And so I'm going to talk more about concurrency and what to characterize it, but I would say that there are two general ways to approach concurrency, because of course many people have looked into this issue of how to program concurrently. One approach is to say, well, concurrency is the general case, so sequential programming is just a little special case, so let's program concurrent from the start, which is very elegant and convincing intellectually, but there's also another approach which says we understand sequential programming, so let's keep close to what we understand. And this is really the approach used in Scoop. It doesn't claim that everything is concurrent. We should be starting from concurrent concepts and then treat sequential as this tiny little special case. It says we understand sequential sequential programming, or at least we understand it much better than anything else. We have ways to reason about sequential programs, both informal and formal. So let's try to remain as close as possible to the modes of reasoning that we do understand. And if you think of analogies in other disciplines, you could also say relativity is the general case. So let's teach everyone relativity when we teach them elementary physics, and then after 10 years of studying relativity, they'll be given the special case of Newton's mechanics. And of course, it's not the way it works. We study classical mechanics, and we understand relativity as an extension to classical mechanics. At least that's. To the extent that the metaphor applies, that's what it teaches us. And here it's going to be the same. So the key property that I'm going to try to retain is what may be called reasonability. Now, it's not an English word. I don't think it exists in the dictionary, but what it says is clear. It's the ability to reason about programs. We know how to reason about sequential programs, and we would like as much as possible to be able to reason about concurrent programs as well. It's interesting here to look into some of what others have said. Now, one thing I could do, but I don't have the time to, is to justify concurrency. Clearly, the justification is the evolution of the IT industry with the end of Moore's law as we knew it, the flattening out of CPU performance improvement, and clearly we know that in order to continue obtaining the kind of improvements of performance that we have obtained over the past decades, the only way to get them is to do several things at once, to use concurrency and parallelism. So one would need to justify all this through curves of CPU performance and other such graphs. I'm going to skip that part. I'm going to take it for granted. And if you read this report, this extract from a report of the US National Academies of Science, you see the real challenge that we are trying to cope with here. The only foreseeable way, the right to continue advancing performance is, as I just said, to match parallel hardware with parallel software. So there has been genuine progress, such as some scientific applications. Heroic programmers can exploit vast amount of parallelism. So however, none of those developments comes close to what we need. So the key word here is heroic. At the beginning of the computer age, just to be able to program any application required heroes. Very few people are able to do it. And then little by little, we learned, we developed methods, we developed tools, we developed languages, and you can program good applications today, you can significant applications well, without being a hero. And what this extract is saying is that for concurrent programming, we are back to square one. We're back to the 50s or 60s, where really one had to be a hero to be able to produce any kind of program at all. So for concurrent programming, all bets are off. Now, to understand this a bit further, it's useful to go back to Dijkstra and in an extract of his famous article on the go-to considered harmful, which I'm sure many of you know. So this is a paper that criticized the use of the go-to instruction, but I'm referring to it here not so much for the go-to as for the underlying intellectual challenge that Dijkstra describes and his reason for discarding the go-to. He wrote, "Our intellectual powers are geared to visualize static relations, not processes evolving in time." So we know pretty well to model static things, but when it comes to the execution of a computer program, rather the executions, the zillions of executions, or the infinity of possible executions of a computer program, it becomes extremely hard, and we're not equipped for that. So he describes the fundamental problem of programming as bridging the gap, the conceptual gap between the static program, the text of the program, and the dynamic process, that is to say, the zillions of executions of programs. And of course, in the case of concurrent program, this space of dynamic executions is even bigger. So these words of Dijkstra are more timely than ever. And to give you an idea of the kind of thing that we deal with, Here is the standard dining philosophers solution. So the dining philosophers, as I'm sure many of you know, is this academic example which is very useful to model many problems of resource contention in operating systems, for example, where you have a number of people sitting around a table and eating spaghetti, and in order to eat spaghetti, they have to pick up 2 forks, and so if you're not careful, at time t equals 0, every diner, called a philosopher, picks up his or her right fork, and then at time t equals 1, they only want to pick up their left fork, but of course it's taken, and you get into a deadlock, and of course there are all kinds of solutions available to avoid this, all kinds of algorithms. So the typical algorithm taken from a standard textbook, a very good textbook on operating system by Tannenbaum is like this, is the one shown here, relying on semaphores and that kind of techniques. And it's really the go-to. It's really the go-to in the sense that in order to understand this kind of program, you have to think like a computer. You have to turn into a computer. And it's even worse than the go-to, because the go-to forces you to go back and forth in the program to understand what's going on. But here you have to go, on top of that, back and forth between different processes. And so this is at a very low level of abstraction, and the gap between what Dijkstra called the static view and the dynamic view, this conceptual gap is enormous. And if you look at the state of the art today, this is what it is. If you go to the dining philosophers page in the great Rosetta Code page, which has solutions to many problems of programming in various languages. So, if you look at the C solution, it's that kind of thing, as we just saw, very low level, manipulating semaphores, mutexes, and such. If you go, I'm not going to take many examples, but if you go to the Python page, it's the same. It's extremely low level. So this is not appropriate for solving the kind of difficult, complex problems in difficult and complex systems that we have to do today. And so, just as an anticipation as to what is coming in the presentation of Scoop, this is the way you would do it in Scoop. And fundamentally, what you do is give me my left fork and my right fork, like eat of left and right. And the key word is separate. And so, at this point, is basically magic, and I will explain the magic as we go. Here's another example of the kind of problems that we are facing in programming concurrent applications. So I want to transfer a certain amount from a certain source account to a certain target account, and this is the way I would write it. I would have a pre and a post condition, but let me simplify it to the bare essentials. Basically, what I'm going to do is, if there is enough money on the account, then withdraw the amount from the source and deposit it to the target. And one thing I should have mentioned is that, of course, the basic constraint is that the amount, the balance of a bank account should never go below 0, and this seems to guarantee it. On the other hand, you can see catastrophe brewing. Let's assume that we have the situation here with 3 bank accounts, Jane, Jill, and Joan, with $100 on Jane's account and 0 on the others, and we want to someone wants to transfer $100 from Jane to Jill, someone else wants to transfer $100 from Jane to Joan, and so you see what might happen once in a while. The first call comes and says, sure, fine, great, there's enough, there's exactly $100, we're in luck today. The second one comes and makes the same assessment, great, we can move on, and so they both move on, and we end up, of course, with exactly what we didn't want to achieve in the first place, that is to say, a value of minus 100. The trouble with this kind of thing and the difficulty of concurrent programming and concurrent debugging in particular is that typically such a situation will appear very rarely, will happen very rarely. So it's quite possible that you've tested your software extensively and everything was fine, and then in the field after 3 months of operation, suddenly something like this happens. So how do we avoid it? By the way, more fundamentally, behind a case like this is the inability to use standard modes of reasoning. The standard mode of reasoning is that if we have been given the specification, the API of a routine like transfer, then we can rely on it. It says if there's enough money on the account, on the source account, then we can actually apply the operation, and we are going to get the source and the target updated. But of course, as we've seen, the problem is that in between, some little demon can come in, and by virtue of some artifact of scheduling, will mess things up. So basically, the pillars of civilization fall down. We cannot anymore rely on the assumptions on which we were relying. And so actually, once again, the scoop solution in a case like this is going to be very simple. Just use the keyword separate, as we are going to see. So now it's time to get into how Scoop addresses these issues, and I'm going to describe the mechanisms of Scoop as a successive set of choices, the 10 choices shown here. I'm going to examine them one after the other. So, of course, I could throw at you all the Scoop mechanisms, like the syntax and semantics of a programming language, but that's not what I want to do. I want to take you along the intellectual path which led to the design of Scoop as it is, so that you can see the explicit choices that we faced at every step, and see if you agree with the choices we made or disagree, so that even if you disagree with some of them, I hope you will have learned something. The first choice was to rely on object-oriented programming, so this is kind of a no-brainer. Object-oriented programming has really conquered the world, and for a good reason. I think it's Grady Booch who said at some point that for big systems, big complex systems, there's simply no other game in town. So in the case of concurrency, it's fair to mention that there have been a number of approaches to concurrency that have relied on functional languages, which are kind of a competing approach. Here, my view is that object-oriented programming somehow subsumes functional programming. It's much better equipped to deal with large systems, with questions of structure and modularity, and then you can do functional programming from within an object-oriented language, not really the other way around. So what we retain from object-oriented programming is, in fact, everything, but in particular, the notion of class, which serves as type and module structure, the notion of object, of course, dynamically, and then the inheritance mechanism for reuse and polymorphism and dynamic binding. In the second choice, we analyze what makes the difference between sequential and concurrent programming. So the picture on the right shows the troika, so to speak, of programming, of computing. Computing consists of applying certain actions to certain data structures, which we can call objects. And of course, to do this, we need a processor. In object-oriented programming, the originality is that it's the objects that determine the software structure, at least the object types, and the actions are attached to the objects rather than the other way around. So we need a processor to do this, to apply the actions to the objects. In sequential programming, we have one processor, it's the computer, so we don't pay particular attention to it. And the difference with concurrent programming is that now we are going to say we look at the processor, and in fact we can have any number of processors. So here we identify the fundamental difference between sequential and concurrent programming in this notion of processor. What is a processor? It's a mechanism that is able to execute a sequence of instructions in order. So the processor itself is always sequential. The concurrency comes from the ability to have any number of processors. Processor doesn't necessarily mean physical processor. It can mean any mechanism that has the properties that I just gave, executing instructions sequentially. So it could be a CPU, it could be a physical processor, but it could also be a process on an operating system, or more commonly these days, a thread. Okay? So Scoop doesn't specify what exactly a processor is, apart from the general properties, and then it can be adapted to implementations using different underlying mechanisms. At the moment, the current scoop implementation uses threads as processors. The third choice is to map the object structure to the processor structure quite closely. This is where scoop departs fairly fundamentally from the dominant technique used today to program concurrent applications, which is threading libraries like Java threads or .NET threads, or in the Eiffel world, Eiffel threads. There's a library which does that. And so in those approaches, the concurrency comes from a threading library, but it's not directly connected to the object-oriented structure. So here we're going to connect the two in the following way. We consider the fundamental operation of object-oriented programming, which is take an object known under a name, say X, and apply to it a certain operation, say R, possibly with some argument. So this is what our programs, our object-oriented programs, do from morning to dusk and from dusk to morning. They apply operations, also known as features, also known as methods, also known as routines, to objects. This is also known as a qualified call. Sometimes it's known as message passing, as in Smalltalk. So at execution time, we're going to have a set of objects. And so, for example, OA is one of these objects, OB is another one, and on behalf of OA, we will execute things like x.r, where x, for example, is a reference to the object OB. So this is the essence of object-oriented computation. What's going to change in an object-oriented context is, at least in scoop, is that we are going to have, as we just saw, a number of processors, and each object is going to be associated with a certain processor. So we divide objects into a partition, into regions, each region being in a one-to-one correspondence with a processor. So here we have regions A, B, C, and D. You can see that OA is in A and OB is in B. So we have here a call which is executed on behalf of A, of an object in region A, and which actually targets an object in the region B. And such a call is going to be executed by a processor. Of course, every operation has to be executed by some processor. And the general idea is that for every region, there is a processor. So for B, there is an associated processor, and a call like this one, x.r, where x is denoting an object of region B, is going to be executed by the B processor. So this is where we get the mapping between the processor structure and the object structure. Now, choice 4 follows from these observations. What happens to a call like, to one of these calls if the two objects, the source object and the target object, are in different regions, handled by different processors? So in a sequential context, there is no particular problem. We have some call x.r of v, and before that there were some previous instructions, and after that there will be some next instructions, but we are not going to execute next until R has executed its body here, whatever the body does. Okay? Because we only have one processor, so we cannot walk and chew gum at the same time. We have to be doing either the computation of the client or the computation of the supplier. So next is not going to proceed until we have fully executed R. Fast forward to a concurrent context, where instead of having one processor, we have any number of processors, and for example, the client and the supplier, in this case, could be in different regions handled by different processors. So here, of course, we don't want to wait anymore, because if we always waited before executing next until we have executed R, then there would be no point in having several processors. We might just as well try to buy the fastest processor available instead of having several. So actually, we want to move on with the next instructions without waiting. And so this is going to be the fundamental semantic difference. We say that a call is going to be asynchronous. So one way of saying this is that we now distinguish between a call of a routine and an application of the routine. So on the side of the client, we have a call. This thing here, x.r of v, this is a call. And from the viewpoint of the client, it's just like logging a certain request. On the side of the supplier, we have the actual execution, which is the application of the routine. So in sequential programming, this distinction was not interesting because when we perform a call, we immediately proceed with the application. But in asynchronous concurrent programming, that's not the case anymore. We can log the call and then move on with the rest of our business, next as it's called here. And then sometime later, R will execute its body. So there's this new distinction between call and application. Of course, it's not the case that everything goes. We still need to have some rules of integrity, and there are two rules, two semantic guarantees. The first rule is that for a given call, like x.r, the application occurs after the call. Okay, there is no way to reverse that order. It would make no sense. And the second rule governs the interaction between two given processors. So if we have calls from P to Q, asynchronous calls from P to Q, then between those two processes, the various calls are going to be executed in that order. So if I tell the Tokyo Stock Exchange, sell 1,000 IBM shares, and then later buy 500 IBM shares, and then later to the same Tokyo Stock Exchange sell 1,000 Google shares, and so on. These operations are going to be executed in order because we are talking about calls and applications between two given processes. On the other hand, we do not have any such guarantee between three or more processes. So if I'm sending orders to the Tokyo, New York, and Frankfurt stock exchanges, then of course they may appear in any order subject to the previous two rules, but no other. So now we have two kinds of call. When I say x.r, it can be synchronous if we are in the same processor, or it can be asynchronous if they are on different processors. Of course, if we have such a fundamental semantic difference, it should also be captured by the language. So this is where the only language extension comes. It's the declaration of separate. By the way, when I talk about language, I mean IFOL, but there have been a number of scoop-like additions to various other languages. For this discussion, I'm going to stick to IFOL. So in IFOL, you should declare X as being of type T. It means it has to be handled by the same processor. If you declare it as separate T, it means it could be in a different processor. And then, of course, the semantic of calls is asynchronous. So let me do a little demo at this point to break a little bit the succession of slides. I'm going to build a little email system, which is very simple. I have a client, an email client, and then I have a downloader, which is in charge of downloading messages, and a viewer, which is like, think of the Outlook mail viewer. It enables a user to look at email messages. And of course, it's not going to be real email. I'm going to simulate all of this by having a process that essentially creates email messages and puts them on the client side into a linked list of strings. Each message is going to be a string. So first, here is a completely sequential version. So I can give you a little glimpse of the program. I've written it before, of course, to save time. So there's nothing concurrent at this point. Actually, there is the concurrent stuff, but it's been commented out with these ACM comments. So in the client, there is a downloader and a viewer, and then there's live, which says start the downloader, start the viewer. That's essentially the downloader has this, so it knows about its client, and its live procedure is going repeatedly using some random generation for the intervals so that it waits a few seconds in between, it's going to download a message, and then it waits a little bit until the next one. And then the viewer simulates a user who decides arbitrarily to request a certain next message. So it's like me sitting in my Outlook window, in front of my Outlook window, and I decide to read a certain email message, but the message might not be there yet. So at this point, it's completely sequential. So let me make sure that the number of messages is not too big. No, it's just 10, so it's fine. So it's going to run in a very uninteresting way, because since there's no concurrency, although the viewer says from the start, I want this and that message, in fact, we are going to have to download all the messages first, and then we have the viewer who says, I want message 1, I get it. I want message 4, I get it. It's an arbitrary order, but there's no way we can get messages until they've all been downloaded. So now I'm going to correct this by making everything separate. So this is where I cheated by preparing everything ahead of time. So separate means they are going to run in different threads. Here I'm accessing the viewer and the downloader. Okay, so yeah, this should be also uncommented. This should not be there anymore. And add, same thing, takes a separate instead of a string. So the string lies elsewhere. So if I try to compile this, I think it's not going to compile because not everything is separate. So I need to fix the other classes as well. Let me just make sure. Yeah, there's still this one, which should be the downloader. And now the downloader and the viewer should now be separate. This is what changes. Okay, and I think this is all I have in this particular class. Okay, so in the downloader, there's also stuff that should be separate. You see, these are the only things that change. Now I'm declaring things as separate. Okay. Okay, is that it? Almost. The client is separate, so we have to declare this properly. And same thing for the viewer, and we should be okay. Okay, it's essentially the same thing for the viewer. The client is now separate. Make, which creates, this is the constructor that takes a separate, now it takes a separate client, and same thing for ith. The string is now separate. And we should be there. Okay, let's see if it compiles. Yes, and now let's run it again. And now you can see that, of course, it's what we want. So the order is arbitrary. It depends on my on the scheduling on my computer, also on the random number generators that I chose. So the downloader creates a message, and the viewer wants message number 1 and gets it right away. And now it wants the message number 4, but it has not been generated yet. So we have to wait until the downloader adds message 2, 3, and 4, and now the viewer can read message 4, the downloader adds message 5, and the viewer wants message number 6, which is not there yet, but is going to be there soon. So now we have a truly concurrent system, and you can see how simple the change was from the somewhat silly and monolithic sequential version to the I was going to say the separate version, the concurrent version. Basically, we make a few things that were not separate, we now make them separate. Okay, so let me, so this is the situation that we have now in the concurrent version. We have now put the three objects, the client, the viewer, and the downloader in separate regions. The next choice is a little bit more trivial. It's important in practice. By trivial, I mean more implementation-oriented. It's how we actually get processors. So it's very simple. If X is declared of type separate T, if I create an X, so for those of you who are C++, Java, or C# programmers, this is like a new, it creates an object. Well, it does the same as before, as in sequential programming, except that in addition, it actually starts a new processor in a new region. Now, it doesn't necessarily mean, if you're concerned about the performance, it doesn't necessarily mean that we start a new thread. There are all kinds of optimizations there in the compiler. It can use a thread pool. Remember, a processor is an abstract notion. It doesn't exactly have to be a thread, but that's the idea. That's how we get new processors. Next choice, there's 4 to come. Mutual exclusion on objects. So here this was a very strong decision, and of course carefully weighed to avoid mutual exclusion. So what we wanted to avoid is this kind of situation. For those of you who are interested in formal views, I left on the slide for later perusal the formal variant of this in the form of hostile inference rules that I'm not going to comment. But we can do it in a completely informal way. Let's assume that we allowed interleaving on a given object. Basically what the formal stuff means is that we cannot reason anymore about classes, because the way we reason about the correctness of classes is that we look at the various methods of a class and we look at each one of them independently, and the correctness of the class is essentially the union of the correctness, the addition of the correctness of all its methods. If we allow interleaving on a given object, then it becomes a combinatorial explosion of cases to consider, and it becomes just impossible. Remember this criterion of what I call reasonability. So we are going to prevent this and force the various clients to act on an object at disjoint times. How does it work in practice? Well, the next language mechanism, which is quite specific to Scoop, and I would say quite powerful expressively, is multiple simultaneous object reservation. So it's very simple. It says that if we have a call like this, with arguments A1, A2, and others, which are all separate, we are only concerned about the separate arguments here, then the call is not going to proceed until we have reserved, until we have got hold of all the corresponding objects. So we need all of them. You know, we might need the printer and the network and the mouse, and we say, I want all of them. So that guarantees the mutual exclusion property that was discussed in choice 6. And it's also a quite powerful mechanism to lock in a single instruction any number of objects. So if you remember the dining philosopher's example, this was a trick here, is that I say eat of left and right. Left and right are separate arguments of type fork. And when I say eat of left and right, I guarantee that when the application of eat, remember this notion of application proceeds, which is this code here. Okay, pick my left fork, eat, pick my right fork, and so on. Then I have exclusive access to L and R. And of course, the implementation there is quite sophisticated. I mentioned before that it guarantees fairness. And this is the key to the simplicity of the programming of many applications with Scoop. So as another example of mutual exclusion, it is almost trivial to program a consumer-producer application in Scoop, because basically what you say for the producer, I want to grab the buffer. What's a buffer? It's a separate queue. And the other way around for the consumer. You can also use inheritance here. So if we want to abstract a little bit from the philosopher case to the notion of process, we use the library class process, which has these mechanisms built in. I'm not going to go into the details here, but I'm mentioning it because many people who have worked in concurrent object-oriented programming have claimed that inheritance is an obstacle. It clashes with concurrent mechanisms, and in fact it doesn't. It actually helps us. Choice 8, forced encapsulation. So, just a moment ago, in the last choice, in choice 7, we saw that when we have a number of separate objects, A1, A2, and so on, we can reserve them, we can get hold of them by this call. But actually it goes beyond that. It's actually more restrictive than that, and if you're shocked by the rule I'm going to give, you're not the first, because almost everyone who sees this rule for the first time is shocked, including me, I guess, the first time, but it turned out to be very productive. So it is not permitted if buff is a variable of type separate queue, in general of a separate type. It is not permitted to write this, buff.put or another one. Okay? Why? Well, it's because it's dangerous, right? It's dangerous psychologically, because here, for example, it's very natural to think that value, if it's a FIFO, first in, first out structure, you will have put value 1 and then value 2 next to it. And it's not true, because once again, we can have our little scheduler demons who mess up with the whole thing. And so it's so dangerous that we felt we had to do something to prevent this. And so the rule is that if the target of a separate, if we have a separate call, if we have a call whose target is separate, then it must be an argument of the formal, of the enclosing routine. So in this example, we need to have buff as a formal argument of the enclosing routine, and then it means that when we call insert, then we have buff for ourselves, and then we're sure that what we read is what we see is what we get. So again, it's this Dijkstra thing about narrowing the gap between what we read in the program text and what's going to happen at runtime. Now, as a technical point, this rule favors the writing of fairly many wrappers, like this insert thing. So sometimes you don't want to write a routine like this. So there's a syntactical abbreviation, which is that instead of writing a separate routine, you can write it like this, which was actually the case in the email client example. So it's exactly the same thing. I reserve buff, but instead of writing a routine for this, I use this construct. Last two choices. You might have been asking, okay, we have all these asynchronous calls. It's great. They all go off on their own. And but how do we resynchronize? Because it's very nice to say, okay, Tokyo, you do this, New York, you do that, Frankfurt, you do this, but or even a single one, Tokyo buy, Tokyo sell, Tokyo transfer. At some point, all this synchrony is great, but we need to resynchronize. So you might think that there is a resynchronization instruction, but that's not the case. The way it works is very simple. It's through the distinction between commands and queries. So a command is like a procedure. It does something. It doesn't return a result. A query is like a function. Okay? It returns a result. So here you can see that if X is separate, we start a command, command 1, we start command 2, we start command 3, and they all go off asynchronously. We know that since it's the same X, assuming X doesn't change, we know that they're going to be applied in the order given, right? And then at some point, I want to know the status of my portfolio, for example, in my stock trading example. Tokyo, give me my portfolio. So this is going to be a query, and then we are going to block, so to speak. We're going to. So that is the rule. The client will wait when and only when it needs to, and this means on a query. So the full rule is that a command call is asynchronous from the notion of wait by necessity developed by Dennis Caramel, who is a professor at the University of Nice. Final choice, also prepare to be shocked, because most people who see this are shocked. Actually, it took me many months to accept the evidence that was staring in my face here. The point is this. Okay, I mentioned working from APIs, right? We have to believe APIs. So in a situation like this, in sequential programming, ignore the separate. Let's assume this is sequential. No, I want to use this insertion operation into a queue. And I have this specification here which says if the queue is not full, then you're permitted to insert. And so I do this. Okay, I have my queue, and for example, I test for the buffer not full. And then I'm okay. Well, forget about it. In concurrent programming, most of the time I'm okay, which is actually the worst case because it's not going to be, typically it's not going to be caught in testing. So most of the time I'm okay, but one time in a million, the scheduler is going to make sure to schedule someone else at this point, and the test I'm making is of no use. Okay? So it took me a long time to accept that preconditions cannot be correctness conditions anymore in a concurrent context. It's very hard to accept, but there's no point in having correctness conditions that you cannot trust. So if it's not a correctness condition, what is it? Well, it's a wait condition. That's the only interpretation that we can give. Now, the part where usually people are shocked is that the semantics of non-separate conditions, like the second one here, v greater than 0, where v is an integer, doesn't change. It still remains a correct condition because, either v is positive now or you can wait forever. It's not going to become positive. But the first one is a wait condition, and this is the way Scoop deals with waiting on a certain condition. And of course, this goes with the previous mechanisms in the sense that you can wait on several objects satisfying several conditions. So it's a very general mechanism that gives you a completely general waiting scheme. And for example, in the case of the bank account, this is what we would do, right? We say, I want to transfer when and if the balance of the source is going to be equal to the amount. Let me give you very quickly an example of something that we built, that a student, Ganesh Ramanathan, built. It's a little hexapod. Here somewhere I have actually Ganesh showing the robot, and so you see how it moves. I hope you see.
And you can see that the protraction of this and retraction of this is everything.
And so he found this in the kind of journal that computer scientists typically don't read, arthropod structure and development, with rules. So you see the two groups of 3 legs, which are partner legs. The green are the partners of the red, with rules like this. In the paper, protraction can start only if partner group on ground. So he saw this, and the reaction was, well, this is made for Scoop, right? So this is the Scoop implementation, where basically you have these rules. Protraction can start only if partner group is retracted. So my group, dot legs retracted, and so on. These become the wait conditions. And what you saw, the little demo, the 5-second demo that I showed, is exactly this program. We also wrote it using multi-threading libraries. I don't know about you, but once I've seen that version, I really don't want to go into this world ever again. Let me conclude by mentioning one point that is worth, that is, I think, that is of some interest and on which you can read. It's the notion of traitor. Okay? It's one of the issues that had to be addressed, and it's addressed by the OTAP system. Let's assume that we have a situation like this where A and B are non-separate and X and Y are separate. So it's not a problem to assign X to A because X is separate, but it means potentially separate. On the other hand, we don't want to permit B receives Y because it would mean that we have a traitor. A traitor is a variable that says I'm only referring to local objects with synchronous semantics and so on, but like a traitor in war, it actually represents the other side. So this is actually prohibited by the type system, there are also more subtle cases. So let's assume that we have a routine R, which takes a person, not a separate person, a person. And then we do x dot R of A, but you see F is going to get A, which is, so both, neither F nor A are separate. Okay, they're both non-separate person. But dynamically, since we're calling on X, F is actually a reference to the other side, and so this would be a traitor. So the type system developed by Piotr Nenaltowski in his thesis handles these issues in a very general, very consistent, very elegant way. Okay, so I should point out that what I presented, I mean, I'm just the loudspeaker, so, the portavoce, and this is the result of teamwork with a lot of very bright, very dedicated, and very friendly people at ETH, at Eiffel Software, but also colleagues from other institutions. There are some open issues that remain. Multiple readers are not well taken care of. The implementation is solid and effective and efficient, but it needs better support for distribution. We've done some work on GPU implementation, which requires more, and more on deadlock analysis. And there's more to be done on the theory. And I can conclude with my opening slide, which I will not read again. I will just let you read it again. These are the claims that Scoop makes, and for which I hope I have provided a few arguments. And there's lots of Scoop documentation available at the two URLs that you see at the bottom of this slide.
Thank you, Bertrand. We have a few minutes for a couple of questions. So let me ask the question I have here. Well, at first, the first one is a comment. There are a couple of attendees asking for the source code and the demo to try out what you have shown. So I hope this can be done easily, right?
Yeah, so I'll make the source code available in the next couple of days. And so I don't know what the best is. So if you're registered to the webinar, I'm sure Mr. Timanowski can send you an email with the pointers. I should have made it available ahead of time. I didn't, but of course it is available, and I'll make it public.
Then there are a few questions concerning the relationship between your work and other works. For instance, one question is what's the main difference between Scoop model and the actor model?
Yeah, the actor model is based on the notion of active objects. In Scoop, I mean the equivalent of active objects in the functional context. Scoop actually does not distinguish between active and non-active objects. So, I mean, the full answer would be much longer, because actors is a very interesting model, and when we need to go into the details. But for a short answer, I think this is probably as good as one can get. Give.
Okay, and then, well, another question again related to related work. I will read the question, even though probably I already know the answer, and most of people knows already. How is this any different from using a thread pool and then queuing asynchronous procedure calls?
Yeah, so I'm quite used to questions that are of the form, how is this different from X? But then X can be very different. So sometimes people ask, how is this different from monitors? And then they ask what you just asked. Well, can you repeat again with what the difference with thread pools? Then, how is it different from using synchronized in Java? So obviously, it cannot be the same as all of these. So with respect to a thread pool, I would say the notion of a thread pool is an implementation level notion. And in fact, the Scoop implementation uses thread pools internally. It's just that we provide a model of expression which is at a much higher level and closely integrated with the language. But deep down, of course, whatever concurrent mechanism you use, you are going at some point in the implementation to end up using the same low-level bricks. The difference is in the expressiveness of the programming scheme.
Okay, so I think we have time only for a single further questions, and then maybe I guess there will be a way to provide an answer to the other questions via messages. So the question here is that Scoop seems to be designed for task-based concurrency, and the question is if it is also applicable to database concurrency, like domain decomposition paradigm prevalent in HPC and media applications?
Yeah, that's a good question. I think the assumption that you're making that it's mostly for task-based concurrency was correct initially. We were looking more at the kind of problems that arise in operating systems and networks and so on. However, there are a number of recent developments which I couldn't cover in this survey that go much further into the direction of data concurrency. I mentioned the work on GPUs. There's also work on high-performance matrix computations using Scoop. So it's really trying to address both kinds of concurrency. And the part I showed was more about task concurrency indeed, but it's not limited to that.
Okay, so I'm afraid that we have run out of time today, so thank you, Bertrand, again for this informative presentation, insightful answers to the main questions. And a special thanks to each of you for taking the time to attend and participate today. I'm sorry for the initial audio and video problems, and well, I hope that the recording will be of better quality. So this webinar has been recorded, as we said, and will be available online in a few days at webinar.acm.org. You can find announcements on upcoming webinars and other ACM activities again at learning.acm.org and acm.org. Also, please fill out our quick survey where you can suggest future topics or speakers which you should see on your screen. On behalf of ACM, on behalf also of Bertrand and myself, thanks again for joining us, and I hope you will join us again in the future. And this concludes this webinar. Thank you.